Hello. In this video, we are going to look at our last two convergence tests. Oh, such a relief. I think we're up to like 13 or so right now. These are the last two, the ratio and the root test are what we're going to look at today. And these are some really great ones. They work in a lot of different cases. So very useful tests, and we will be revisiting these in the next unit and using them for power series. So let's start out with the ratio test. Now, the ratio test is a test of a ratio of successive terms. So I am going to take the n plus 1th term over the nth term, and I take the limit as n approaches infinity. And the absolute value is an optional thing in here, but it's a good habit because we're going to need the absolute value version of this for power series. So I tend to just always use the absolute value version of it, which also means that the terms don't have to be positive when you're doing absolute value version of this. So the idea is you take this limit and you see what you get. And if this limit is less than 1, then I can say the series converges. I can even say it absolutely converges if I have the absolute value in there. If I get a value that is greater than 1 or infinity, then the series diverges. Now, the case that is not included here is what happens if it's equal to 1. And this is the only downside of these tests is if the limit equals 1, then the test is inconclusive and I have to use a different test. Okay, so not many of our tests have an inconclusive version of it, but this is one of them, and root test is going to be the same. Okay, so let's give this test a try with an example. These are really great for problems with factorials, which is what that exclamation point is right there. So keep that in mind. If you see a factorial, I almost always instantly go to the ratio test when there's a factorial in there. Okay, so we're going to take and set up that limit, the n plus 1 term over the nth term. And I'm going to have to simplify this. So I flip the bottom fraction and multiply. And it looks something like this. And everything's positive, so I didn't need to continue with the absolute value. And now I have to figure out how to simplify this. Well, in the denominator, if I focus on those 6's first, 6 to the n plus 1 is the same thing as 6 to the n times 6 to the first power. So the 6 to the n's will cancel, and I'll end up with a 6 left over on the bottom. And for the factorials, if you're not familiar with what a factorial does, a factorial means that I'm taking the number in the factorial and multiplying it by every natural number that came before it. So 6 factorial, for instance, would be 6 times 5 times 4 times 3 times 2 times 1. It always goes all the way back to 1, multiplying all those. And there is a key in your calculator. If you're using a graphing calculator, there is a factorial key under the math menu. The probability option is what you're looking for, and you will find the factorial there. So I am going to be able to simplify these factorials. N plus 1 factorial over n factorial. Think about n plus 1 factorial would be n plus 1 times n times the number that comes before n, so n minus 1, n minus 2, all multiplied out. And so really, n plus 1 factorial, I can split off the n plus 1 and rewrite that as n plus 1 times n factorial. And I would get the same thing, which causes the n factorials to cancel out. And then this means, and there's more videos on this that explains it in a little bit more depth than I just did, so definitely check those out. But this is going to simplify to just an n plus 1 on the top, the n factorials canceled, and then that 6 on the bottom. And well, that limit goes to infinity. And so according to the ratio test, when I get infinity for this, it means that the series diverges. So I can say the series diverges by the ratio test. Okay. So that's how this test works. The root test is very similar. The only difference is the setup of the limit is a little bit different. Now, just like with the ratio test, the absolute values are an optional thing. If you add them in there, then you can say absolutely convergent on these. So I'm taking the nth root of the nth term and have the same results. If the result of this limit is less than 1, the series converges. If it's greater than 1 or infinity, the series diverges. And also, if you get exactly 1, then the test is inconclusive and you need to find a different test. So keep that in mind. So the results are exactly the same. It's just the limit that is different on this one. Now, as far as when to use this, this one's a great one to use if you have an nth term that is to the nth power. So if everything in there is to the nth power, when you plug it in here, the nth power and the nth root cancel, and you get something simpler to work with. So that's usually when I use this test. And so here's an example of just that. I have this kind of complicated term in parentheses, and then everything is raised to the nth power, which just increases the complexity of this term, of this series. But doing the root test is going to allow me to get rid of that exponent and deal with something much simpler. So I'm going to set up that limit, the nth root of that nth term. And so the root and the exponent cancel out, and I end up with just 5n over 4n plus 1. And the absolute value even goes away because everything's positive here. And that limit is going to be equal to the limit of the leading terms of the numerator and denominator. So really it just simplifies to 5n over 4n. That plus 1 really does not do much as we go to infinity. And so the n's cancel, and I get 5/4, which is greater than 1. So once again, I get a series that diverges by the root test this time. So that's how these tests work. They're really versatile. You can use them in a lot of situations. They're very helpful. And here are a couple more examples for you to try out. Get some practice with those factorials, with the ratio test, and then with something to the nth power with the root test in number 4. So good luck on those.